Okay, so as I mentioned, just plug in, I mean, so it's unbelievably easy. It's as stupid easy as you can get. It looks like this is going to turn into some hideous nightmare, and it just turns out to be the simplest thing imaginable. Often the case with most theoretical theories, quantum mechanics, every now and then you will actually run into something that looks hard that actually really is freaking hard. That's actually not common. I'm not going to call it rare, but it's not common. Okay, now you may recall the reason is, so I don't like to just say that, is that you do a Taylor series about a value, right? We always expand a function saying that we usually want to center it at 0, or maybe we want to center the function at pi, and do an expansion left and right of that value to using like some offset. Now that concept of an offset doesn't apply to an operator, so that's why the function is set at 0. And again, typical Taylor series, derivative over 1 factorial, which is 1, over 2 factorial, which is 2. But I'm going to stop there. Also, I try not to write operators squared. I try to put them in front of each other. It's better to do it that way. Because think about the homework, what was it, number 3, that you had to do cylindrical? Right, so you can see why you want to kind of be careful with squaring things, right? So I like to do it that way. Okay, now of course I was applying a state to that. I was applying a ket, and that's of course a number. In the example I did, I had momentum, and so I was kind of flipping around like a fish because I was just doing a derivative, and I'm saying, oh, that's momentum, and therefore what's this? Now I like this example because that's kinetic energy. And then for a state, I used e to the ikx. But I realized I had kind of done something stupid because if this is really the momentum operator, I need 1 over I. So I was kind of just really getting stupid there. And then I realized after I was done, I had forgotten h bar. H bar over I. All right. And then I told you, oh, it's atomic units. Atomic units, h bar is 1, which is true. Okay, on your homework, I actually have you, it's a really simple question. I actually show you what atomic units are. And so you'll do, it's not hard. It's a very simple question, but I wanted to show you what atomic units are. So that's number 2 on your homework. And it makes everything easy. You just have to understand energy is now in Hartrees, which you also saw on homework 4, and whatnot. If I kept it, then you get this. And had I not been using it in atomic units. And therefore what you find is, now the thing to look out for is, in your mind, you look at this and that's the operator. Right? No, it's not the operator. The operator's right there. This, in this example, you want to think of this as f of x because that's familiar to you, and it's x squared. Right? X, of course, and of course, what's x? X is the operator. Right? That's how you translate your traditional teaching of mathematics, which is everything is an x and a y, or f of x is y, and all x, y, x, y, x, y. You don't have any more x, y, so you have operators. Okay. So that means that this is really x squared at 0, which is 0, x, 2x at x equals 0 is 0, and on and on and on. So I won't do it, I'm talking about what we did last time. And so therefore, the momentum operator squared on e to the ikx, what, oh, and did I forget a minus sign? I forgot a minus sign. No, the I takes care of it. That's right. K squared e to the h bar squared, not in atomic units. So I'm doing it again. All right. Anyway, so there you go. That's just a reminder. I started out this section with a much more difficult example, and then I didn't do it. I wanted to do this one first, just to remind you what, I just want to give myself a little more room. I mean, you know momentum equals momentum squared. And you are sick to death of momentum squared because it's in the Hamiltonian. Right? So you've seen all that before a zillion times. So now, what about, let's do this one, e to an operator. Right, that was the one I said, like, okay, let's say the operator is the derivative, let's e to the derivative. So let's actually do that one. I did that simpler one first. All right, remember the function is e to the x, where x is 0. So the first term is 1, right? You don't see, it's not 1 times the operator, it's just 1, e to the 0. Operator isn't there. Right now, we have the derivative of e to the x, which is e to the x, at x equals 0, which is still 1. Oh, now we have the operator. And then we got the double derivative of e to the x at x equals 0, which is still 1. Now we got the operator squared over 2, and blah, blah, blah. Now, what you end up with is and don't forget that your state is actually still there, right? Eigenvalue equation, the state doesn't go away. So there you go. So that's how you do it. And this guy is actually terribly important. Let me go ahead and foreshadow, because we're going to be spending about 2 weeks. I'm going to introduce time-dependent quantum mechanics in this class because in some universities, like the one I went to, you have 1 semester of what we're doing right now, and then you have another full semester of time-dependent quantum. But we don't do that here. Time-dependent quantum is kind of folded into spectroscopy. So that's great, but I know some of you may not end up taking it. So let me point out. So we're going to go ahead and do a little time-dependent quantum. And if you take the spec class and you're well prepared, and if not, then it's good that you've seen it. Okay, e to the I Hamiltonian time over h bar, and energy times time is joule seconds. H bar has units of joule seconds, and I always look for that. I always make sure my units cancel. The eigenfunction of a Hamiltonian I usually call a wave function psi. So that implies that this is the eigen state of the Hamiltonian, and that would of course be equal to e to the sorry, there's a minus sign there. I forget that all the time. Okay, so remember, energy is a number. It's an electron volt. 10 to the minus 18 joules. Okay. Times the wave function. Okay. Now, what this is actually time-dependent quantum mechanics. This is a wave function at time 0, and all of this is a wave function at time t. So this is the time evolution operator. So that's why this stuff is important, is because this is how things evolve in time. Okay? So this is really important. Really, really important. We're going to spend 2 weeks on it. So I just want to let you know that that's why I did all this. We're also going to look at, now let me also tell you a little bit about transposes. Now remember, a transpose of an operator, let me just remind you that an operator is meant to act on a ket. And let's act on an eigenstate, because that makes the most sense. It's easier. The dual correspondence thing is this. If you have a bra, then you need to be acting, bras are acted upon the other direction. The operator needs to be the transpose, and I think you get the complex conjugate. There you go. Okay. So transposes. I mentioned to you that they're not complex conjugates. The transpose is something different. Now that I've shown you what this is, and again, I'm kind of foreshadowing you, I can show you what a transpose looks like. Now, I told you that I couldn't really define a transpose, and I largely can't, but I do have a couple of examples. Okay, so this is the example of a transpose of actually the function of an operator, but that's still an operator. This is the time evolution operator. Okay, you may notice that I simply made the complex conjugate, right? Okay, so I said before that a transpose is not a complex conjugate. You have to figure it out by other means. I can't give you a formula for it, right? So every system is different. You have to figure out what the transpose is. Here, the transpose has to be the complex conjugate. Now that is an accident. It turns out that when we get to time-dependent quantum mechanics, the operator times its transpose has got to equal the number 1. That is the rule for time quantum mechanics, and we're going to cover that. What it means is that if the state is normalized, it needs to, if it's normalized at time 0, it will be normalized at time t. So therefore, the operator times its transpose better equal to 1, and given the form of this times that is 1, right? Equal to 0. Anyway, now again, I'm kind of being stupid here, showing you stuff that I'm going to talk about in 2 weeks, but it was just kind of a good time. I really like to show you things ahead of time so that when we see them technically for the first time, it's not going to blow your head off. Anyway, okay, so today, I haven't really even started talking about what I'm supposed to talk about today, which is more on Dirac. And this, what I'm going to cover today, should get you through questions 1 through 6 of your homework. So that's what I'm trying to do. And I'm trying to emphasize the matrix representation of Dirac. Dirac is really inherently a matrix representation of quantum mechanics. Let's look at this one. So we saw this last time. And what I'm doing here is I'm expanding a state gamma, which is maybe a wave function drawn by a cat. It could be anything. So some squiggly lines between 0 and L, where that's a trap. So I got a particle in a box potential. I got my kitty, and I taped a pen to her head, and she drew something. Okay, that's fine. It's weird, but fine. And what I've got on top of that is the basis set of particle in a box wave functions. So that would be the A's, and the gamma is the kitty thing. All right, so I've done that a zillion times. All right, now let me give you the highfalutin sounding smart words of Albert Einstein, who would describe this in a talk. And then let me tell you what it really is. The high speech is that this is the representation of gamma in the alpha, the A basis set. Okay, again, is the representation of the state gamma in the A basis set. Maybe I should say alpha basis set, because now I can speak more brief. Okay, now what it means is, in a matrix representation is this. So this is how, I should, you know what, let me not use dashes, let me use numbers. Now that's not out, I'm saying alpha, it's gamma. Okay, now let me explain a little bit what's happening here. Okay, so what you're seeing here is again, let's call it a wave function, but it's drawn by a cat, so I don't know what I can really do with that. So I understand particle in the box wave function, so I'm going to represent it as, I'm going to represent it in the particle in the box basis set. Again, that's the highfalutin words. Okay, what does this mean? Now notice I switched from dashes to numbers. Remember that the dash or double dash in the book, and I'm going to try to use the book because that's what you have. That's just an index, like from I equals 1 to n, from j equals 1 to n. Okay, but just like I and j are really 1, 2, 3, I'm using 1, 2, 3. What does that mean? Ground state, first excited state, second excited state, and on and on. I don't have to order them that way, but why wouldn't I? Right? Ground state, first excited state, second excited state. Cat, cat, cat. Inner product is the projection of that state onto the particle in the box state. So if Kitty happened to have done this, then this is 1. That's what Kitty drew. And of course, the particle in the box state is a half sign. And then all the subsequent vectors, components, would be 0. Right? Because if Kitty happened to have drawn perfectly the ground state, then the inner product, the projection of Kitty's state to the ground state is perfect. It's 1. And that means that it doesn't look anything like the others. So those projections are 0. So anyway, that gives you an idea what this looks like. So the representation is as a column. So math speak, hopefully I'm getting this right. That's not a matrix. It technically is a matrix, but we don't call it a matrix because there's only one column. When it's one column matrix, we call it a vector. It's still a matrix, it's just a one column matrix, but we call it a vector. So that is a column vector, right? So kets are column vectors once projected into a basis set. Okay. So now, all right, I hope this is kind of rather brainless. Remember, give you an example. Here, let's actually look at some Stern-Gerlach if that's what you're doing on your homework. Let's do a little Stern-Gerlach thing, and what have I done here? Okay, let's say that we have some Ag ions and they're in the Sz plus state, so they've already gone through a Stern-Gerlach device. And this Stern-Gerlach will be in the X direction. And it looks like it's got a block for the minus Sx, and so it allows the plus Sx to pass. Again, using the Wilks notation. Okay, so it'll allow that to pass. Okay. Now, heads up, and try not to, I try to walk you through this on the homework, so I'm kind of giving you some answers ahead of time. The device is an operator. The operator in this case would be Sx plus. It's actually the projection operator onto the Sx plus state. That's what you call that. That's an operator. It's called a projection operator. Given that the final state is Sx plus, which I see right there, is the Sx plus projection operator. That's what it is. Okay, now hint on your homework. Remember that you're working in the Sz basis set. So the way you deal with this is you project, you're going to change Sx plus to Sz. It needs to be the Sc basis set. And so I'm turning this bra into an Sc basis set bra. Okay. And the reason is that you want to see what happens to the input. The input is to the right. So the input state, which is Sc plus, that's the input. This is the effect of the operator. And then, of course, the final state is exactly what I said it is. Sorry, that's kind of miserable. There we go. So that's how you deal. So anyway, just some homework stuff. Okay, I'm bringing this up to make sure that you're okay with bras and kets and whatnot. Let me show you now how to deal with a bra. All right, so you talked about kets, they're column vectors. What about a bra? Of course, it's going to be a row vector. All right, to deal with this, to help you understand why a bra goes the other way, is let me act on a state with an operator. And what the point of all this is, for one, to help you with your homework a little bit, but also to point out that operators turn states into other states. while spitting out some measurable. They always do that. They don't, you may think like, oh no, the state's gone. No, it's not gone. That would destroy matter and energy. Right? It just turns it into something else. So remember, operators measure things. The measurement's the eigenvalue. But to measure something, you have to change it, right? That's like one of the things in quantum mechanics you heard about as a kid. If you shine a light on something, it picked up some energy. It went from a ground state to an excited state. I don't know. There's really a million things that could happen to something during a measurement depending on the measurement device. So operators fundamentally give results, eigenvalues. Those are measurables. These are Hermitian operators. This is like a real thing like momentum or energy. But remember that the state itself has been altered. So that's what I've done here. I've taken this input state, this ket, and now it's been turned into a different state. Okay, now why am I saying that? Okay, so therefore, what I'm going to do now is I'm going to project, using the book's notation, I'm going to project one of my basis states, any arbitrary basis state, ground state versus excited state, onto beta. Okay, now why am I doing that? Well, let me insert the definition of beta as the result of the operator acting on state gamma. Initial state, final state. What is the projection of that final state onto a particle in a box? I don't know why I'm asking that, but I am. The final state was actually the initial state operated on by the operator, maybe it's a Stern-Gerlach device. Okay, now that I'm here, I'm still kind of stuck. Now again, this is very abstract, so you probably don't know why I'm stuck, but I am stuck. So the last step is, these are equal. The last step is to resolve an identity. Now you know that, now you can see why I was using a double prime here, because I wanted to resolve an identity and I like using a prime for my identities. So I'm going to, and I have to be careful where I insert it. Now, knowing that I am very well aware of what the particle in a box states are, whatever my basis states are, I know what they are. And again, I'm particle in a box as an example. I am not going to insert the resolution of the identity here. I am not putting it here. I'm going to instead put it here. Okay. Now, why am I unstuck? Why was I stuck here? Why am I unstuck here? It's because I know what this is. It's right here. Column vector. And again, my kitty drew this state, and I was able to resolve what those coefficients are. It happened to be 1 because kitty drew the ground state, the rest were 0. Okay, so I know what this is. Okay, this is just my operator in the basis set. Now, I kind of have to know what that is. Now, examples include, did we not do an example? I thought we did one example. In fact, I thought we did we not do this example before? No, we did an SZ. We did an SZ operator. And that's what you're doing on your homework, right? So if this was a Z, if this was a Z deal, a Z projection operator in this device, that's its job was to do that. I think we did this, right? I showed you that the matrix representation is 1, 0, 0, 0. Okay, so again, the reason to have done all this is because I know what this is, and this matrix, I know what it is, but it needs to be represented in the correct basis, the basis set that I'm familiar with. And Stern-Gerlach, an SZ projection operator, sorry, this looks kind of awful. I don't need those brackets, I just want you to understand the different ways that they act. Okay. The SZ projection operator is 1, 0, 0, 0. And it will, on your homework, you're actually going to derive this, and I'll show you a little bit more right now. Okay. So just like that example, let's say that the operator matrix is A, B, C, D. Now again, this ket in the basis state is a column vector, a column matrix, we'll call it a vector, and it has to be a new vector. Let's see, AE plus DF. Okay, so again, a ket is transformed into another ket. So if a ket, especially with the spin stuff, is like SC up, SC down, how much operator is still is a 2-element vector. That's still spin up, spin down, having been modified by the effect of an operator, which is a Stern-Gerlach device. Now, again, on your homework, I actually make you derive that, but I showed you the answer. Anyways, whatever. Okay, more practice. Now, I still haven't gotten to what a bra is. Now, a bra is obviously a row vector, but let me prove it. And also, a lot of what I'm doing here is trying to get you used to looking at your app notation and seeing matrices. Okay, so before I had all this in ket space, so let's do it all with bras now. So again, I had my cat state, but for whatever reason, it's now on the other side. And so now the question is, what is this? What happens when I ask for the inner product? What is the inner product of that state with a known matrix element of my basis set? Okay, now again, to solve this, I will resolve the identity. And that's why I use double dash there, because I want to use single dash here. There we go. All right. And, oh, wait a minute. What have I done? I've done something stupid. How do I want to do this? I want to say that that's, no, I can work with this. Sorry. I can work with this, right? No, I'm sorry, I screwed up. What did I do wrong? Sorry. Yeah, I messed up. So I did exactly what I told you not to do before. Sorry about that. I was rushing. With gamma, here's where, so yeah, you see how I screwed that up? I actually inserted the resolution in the wrong spot. And that led me to a place I couldn't go, I couldn't do anything with it. That's how I knew I screwed up. Okay, so now I can do something with this. Actually, I'm kind of at a stopping point here. What I see here is a matrix, and if a matrix is on the right, then a row has to be on the left. So that's one way. Again, I can see here that this is a matrix where the rows are defined by this, and the columns are defined by this. And if this is on the right of it, matrix mechanics requires this to be a column matrix. That's another way I know that this is a column matrix. Now, if I have a matrix on the right, what is to the left of it that has to be a row. Otherwise, the rules of matrix mechanics don't work. The way you multiply these together, it has to be a row. Now, notice that the output is a row vector. A bra. So everything makes sense. Okay. So there you go. So again, the point of this was to make sure you understand that kets should be represented as column vectors and bras are row vectors. And the last bit, I do have another definition of a transpose. So this is the transpose. And this comes up once or twice, so you just want to remember the word. Just remember that a transpose for an operator is pretty different and kind of hard to know what the heck it is. Okay. Anyway, column this, row that. Let's go back and look at the matrix representation of the operator one more time and make sure that you get exactly how to do this. Because again, you're doing this on your homework. You may get a little flummoxed at first, but once you get the hang of it, once it snaps, you've got it. It's like riding a bike. You'll get it for the rest of your life. And it becomes incredibly easy. Now again, by itself, there's no basis. It doesn't live in the particle in the box world, or the harmonic oscillator world, or the hydrogen atom world. Right? Those are all of those problems have an infinite number of states. Those are my basis states. So I'm going to give it a basis state. I have to actually have two resolutions of the identity. I have to have two because I have to have a row and a column because it has to be a matrix. Okay, so now it's in the matrix form. The matrix is really right here. That's the innards of the matrix. The ket on the bra on the right and the ket on the left, those are there just to tell you where in the matrix the element belongs. That's its real job. Just like here, you understand that what I'm saying here, this is the ground state. But here you understand that's the first excited state. You understand that this is the second. Just like that, this is the job to tell you what column you're on, and this tells you what row you're on. That's what its job is. Okay, now that means that the matrix representation is this. And now I'm going to switch to ones and twos. Okay, now, and this is important, this comes up a lot. If you get it switched, the thing is, it actually wouldn't affect the results as long as you switch everything. Okay. I'm not diagonal. Now, if I'm diagonal, this isn't hard. A2 operator in 2. That's easy. Okay. Now, if you get this wrong, and it could be catastrophic if you get this wrong. Which one's which? Is this 1 and 2, or is this 1 and 2? Which is it? All right, both 1, 2. No one? 2, 1? Yeah, 2, 1. Right, now make that 1, 2. And to make sure you get it, 3. Oh, it gets a little ahead. And on 9. This is how you're supposed to do this, by the way. And I messed that up. I always do that. Okay. So there you go. That is how you do direct notation and matrices. Okay. Now, if we've actually already covered this, but it bears repeating. If A's are eigenstates of the operator, that you may recall that, okay, so any matrix element, and I'll just make it generic, A double dash, operator, A dash. This would represent an off-diagonal operator, off-diagonal element, and I'll act on the right on the ket. A prime, that's a number, that's the eigenvalue. And I've got A double prime. I've got the projection of one state onto another state that are not the same states. That's 0. Right, so remember, when states of the same basis are inner product. When you have the inner product of states and you're working in a basis, it's a Kronecker delta. Okay, and what that means is that the operator is looks like this in matrix representation. A1, A2, those are the eigenvalues, A3, and everything else is 0. So it is a diagonal. It is a diagonal matrix. Be careful of the word block diagonal. Block diagonal matrices are not diagonal matrices. Block diagonal is when I would have, these are 0, but they're exactly the same left and right. So that's block diagonal. That is not what we're talking about. Most matrices in quantum mechanics, they're almost always block diagonal. All of them are. But if they are in the world of its eigenstates, then it is truly diagonal. Anything else is 0. Oh God, what am I going to talk about now? Last bit, I guess, let me make sure that do a couple more representations of stuff, more stuff with direct notation in the language of matrices. Let's do a inner product. So let me also emphasize inner products are often what the end goal is of a quantum mechanical calculation. Now, whatever alpha is and beta is, I don't know. But if you're trying to answer a quantum mechanical question, often the final step will be this, and therefore what is it? That is usually whatever you're trying to do is going to turn into. Now, the reason I know that is, knowing what we know now, you should know that the bra is going to be a matrix, a row vector, and the ket is a column vector. Now, the result, the reason I'm saying that this is generally what you're trying to do with quantum mechanics, AC plus BD, is that the end result is a number, right? So now you're seeing, and again, I'm just doing matrix, like whenever you learn matrices like 7th or 8th grade, this is what you learn to do with this stuff. The result is a number. It is no longer, it is outside the world of matrix. No longer a matrix, it's a number. But I already told you an inner product was a number. You're just seeing it in matrix form. It all makes sense. Okay, and again, this is the end goal of quantum mechanics, such that I can't even really think of an example. It really is everything. I'll try to think of an example next time. Okay, tell you what, let's do this same question. Notice that I didn't necessarily use a basis set. So what I would do is it looks like I want to do one resolution of the identity. Okay. Now, in this case, what you now have is, this is something that you got to get used to. You're going to run into this. I want to point out. Okay, so we're going to have, again, we're going to have a row vector for the bra. But I want to point out that I have written them backward. That's a bra, I made it a ket. And I took the complex conjugate. Now, why did I do that? Because this is the most understandable thing that you usually get. Now remember, beta is, so alpha, I guess I called it gamma before, but gamma is a wave function drawn by my cat, and beta is a wave function drawn by my neighbor's cat. And I wanted to know how similar the cats are, and they're quantum mechanical cats. Okay, now we talked about how my cat is a good cat, drew the ground state. And I know the coefficients. And those look like this. I should have used gamma, so I screwed up. And again, A1 is the ground state, A2 is the first excited state, A3 is on and on and on. Okay, again, my cat drew the ground states. That's 1, that makes the rest of them 0. I can understand this quite well. My neighbor's cat, see, the thing is, notice that I've taken these values and I flipped them over and I'm taking the complex conjugate. It's because knowing the projection of the neighbor's cat drawing onto the basis is something that's easy to know. But the converse is actually not, I don't intellectualize it nearly as easily. I totally get projecting something crazy onto something I know. That inherently makes sense to me. This is how data appears in a problem. This is what you experimentally know. It's written the other way. So what I do is I flip it over and I just make sure I take the complex conjugate. So again, I just want to make sure that you know that. Last bit is to note that all operators, since operators ultimately take one state and turn it to another state, and hopefully spit out something that you want, like the energy or the momentum. But fundamentally, they're going to do this. So all operators ultimately look like this. So they convert things to other things. And note that, again, because this isn't an unfamiliar representation, what I want to do is resolve two identities. I'm just restating what I already did. Resolve two identities. Like so. Oops. I get a little bit lost between my greater and less than signs. Here we go. Okay, so now I have that, and as I said before, this is the innards of the matrix right here. Now it looks a little different than what you saw last time. Let me show you what that is. Let's just draw that as a matrix, and this should be more than enough to do problems 1 through 6. Although I know that it's still, what you're going to have a hard time on in the homework is looking at this stuff and then making it work for an actual problem. That's why we have homework. Okay, again, in the matrix representation, sorry, not A, alpha. So be careful with that. Okay. The way this works is an element is like this. And this would be A2. And again, I'm writing this so that I'm always projecting my my unknowns into the knowns. And usually I ought to say you can do four elements so that you can see where your 1s and 2s belong. Okay, and again, what did I flip over? I flipped this over. Notice that? Again, I'm projecting my basis into my cat function. That's weird. I just can't intellectualize that. But I can understand how much of my cat's function is represented by the ground state. Now that just inherently makes sense to me. I know how to calculate that. I just better take the complex conjugate. Now remember, these are separate. That's element 1, 1. That's element 2, 2. That's element 1, 2. That's element 2, 1. I'm sorry, I drew those a little too close together. So this is how you construct a matrix. It's just another way to construct a matrix. Now before you saw I did it this way, element 1, 1, 1, 2, 2, 1, 2, 2. Okay, but when the matrix, when your operator looks like this, then it looks more like this. And that's actually how we do number 4 or 5 on your homework set, by the way. So you're going to go from this representation at the beginning, and then later on, towards the middle of the problem set, then I had to switch it to that representation. It's the same thing. Anyway, I promise I wouldn't keep you so, I'm trying not to keep you so late.